Hello, everybody. We are about to tackle assignment 2. In assignment 2, we are only going to do problem number 1 in this video, and this actually may get split up into 2 pieces because it's going to be long. I figured I'd just go through the problems. It's going to take me a little while, so you will probably want to fast forward to the parts that you need because this is not going to be short. Okay, so let's start. Well, first thing, when you look at these problems, remember we have like a litany of tests that we have to kind of go through in our minds when we kind of start tackling these. And the first thing that has to go through your mind is, remember, does it look like it's approaching 0? Because if it's not approaching 0, you know right away you have the divergence test. So when I look at this, the first thing that I see, okay, ln of n over n, as n is going to infinity, the denominator is definitely going faster than the numerator. It is approaching 0. We have a chance of convergence. Okay, so we have a chance of convergence. What are we going to do? Well, my instinct, though, is that 1 over n diverges, right, by the p-test. So my instinct is ln of n over n probably is going to diverge as well because ln of n is actually going to be greater than 1. In fact, we could use that, right? We could say, hey, the ln of n right? Isn't that usually true? Well, it's true for all n that is greater than or equal to e. So the fact of the matter is, right here we have a 2 over here, right? We have a 2 sitting here saying, well, that means the first one doesn't work. But if we just kind of say, well, I mean, let's be honest, right? We could turn this series into this. Sorry, yeah, this is right. I mean, this is the same thing as this. That should have been a 2. So we could have done that. And then we can just evaluate this and determine whether that converges or diverges. And know that if that converges, adding it to some constant is fine. If it diverges, adding it to some constant is fine. It doesn't make a difference. Really, what we need to evaluate is the question is this, right? We can evaluate that. So we can use this rule, this comparison test. And in fact, we can say that because, we'll go here, because we know that this diverges by the p-test. Right? Diverges by the p-test, and the ln of n over n is greater than 1 over n. Therefore, this diverges. By the comparison test. And that is one way we could have done that, right? But there's another way we could have done it all together. You could have said, well, I didn't do a comparison test. I did something completely different. Well, yes, so did I, right? The thing that I actually did was this. I thought about this, and I thought, hey, these are going to kind of go together. Using the integral test, these are going to converge and diverge together. Oh, sorry, I need to change some letters, right? Otherwise, that doesn't make any sense. All right, let's make some letters that make a little more sense. So now if we want to evaluate this, we can just say, well, let's evaluate the limit as b goes to infinity. If you do a quick u sub, your du is going to be 1 over x dx. So it's basically going to be the integral of u du, which is going to be 1/2 u squared. And I'm just doing that for those of you that wonder where it comes from. But back to where we were. We're basically going to be evaluating 1/2 the ln of x squared from b to 2. And even though it's going there really slowly, this puppy is definitely going to infinity. So therefore, it also diverges by the integral test. You do not need to do both. Frankly, doing both is a huge waste of time. But choose the one you want to do, and make sure your method is, something that you can kind of show evidence for. Wow, this is going to be long. 5 minutes, one problem. Woo! All right. I got coffee. Okay. Again, instincts for me, 2 to the n, getting there pretty fast, exponentially fast. The numerator, not so fast. It's a polynomial. My instinct is converge. Let's see if we can prove it. When I have an exponential function, I love using the ratio test. So the ratio test says, let's look at the one term. Let's find out the limit as n goes to infinity. And we put the actual term on the bottom. And we put the next term on top. And if we think about this for a second, okay, well, this is not too hard, complex fractions. I'm going to reorder, well, maybe I shouldn't the first time. I usually do this in one step, but sorry, I'm going to make this nice and clean. And now I'm going to rewrite it. Awesome. We know that this first term here, this here is going to approach 1. We know this one is going to use our exponential rules. It's just going to turn to 1/2. So this is just 1/2. And therefore, if rho equals 1/2 and it's less than 1 by the root test, I said root test, I meant ratio test. Whoop. We have converges. I'm sure I'm going to do one of these problems and get the wrong answer. So that'll be fun for us to figure out. Factorials love the ratio test. They just love it. The ratio test is just calling to every time you have a factorial. This time I'm going to try and do the flip in 1. Hopefully you'll stick with me. Okay, so I'll write this out first. But then I'm going to do the flip and move things around in one step. And the 10 to the n plus 1 is here. And now the thing that we flipped, I'm going to put the n factorial here, and the 10 to the n here, so it's easier for us to see. So this thing here, whoa, that's no longer just 1, right? That's because that's going to be n plus 1. Remember, n plus 1 factorial is really n plus 1 times n minus 1 times n minus 2, so forth and so on, right? And n factorial is n times n minus 1 times n minus 2, dot, dot. So if you take that and divide them, right, you think what happens, all you're left with is n plus 1. So you're going to have, okay, the limit as n goes to infinity of n plus 1. And what do we have here? Well, that's just 1/10, it looks like. And what does that do, folks? Well, this is just 1/10, but this is getting huge, right? It's getting huge. This is approaching infinity. If it's approaching infinity, we definitely know that the rho is greater than 1, and therefore this is going to diverge by the ratio test. (1D). All right, I'm going to do this one the way that I would probably do it, and then I'm going to get mad at myself because I'm going to realize that doesn't work. Because whenever I have an n here, like whenever I have something here, this tells me try the root test. That's what it tells me. It's like, hey, try the root test. That might work out. So we'll try the root test. And in looking at it pretty quickly, I'm going to see that I'm going to be disappointed, because that's going to turn into this. And then equals 1. And what do we say about the root test, right? If rho equals 1, you know nothing. So our instincts were bad. They usually actually work out, but in this case, our instincts did not work out. We can't use the root test because we know nothing. We have to go back to the drawing board. Okay, well, that's what happens sometimes when we're doing math. We go back to the drawing board, we try again. So I guess we will have to look at this. Wonder what this is doing. Well, probably think about what's happening to this. Does this have a chance of converging? I don't even know if it has a chance of converging. Well, if I think about this for a second, I know that this follows this pattern. And this, by the way, is e to the negative 2. If you're not seeing where this comes from, I've created another video called, I think something about like the definition of e, or reviewing the definition of e. This is something that you should have seen in pre-calculus. Maybe you didn't go through it when you're doing compound interest. Maybe you didn't go through it as much detail. But this is something that comes from, and I kind of redid it again in case it's not something that's fresh in your mind if you're wondering where this comes from. But this is one of the definitions of e. This negative 2 here translates to the negative 2 there. So this e to the negative 2, well, this is what it's approaching, right? This is what the sequence is approaching. The limit, as n goes to infinity, of a sub n doesn't equal 0. It equals 1 over e squared. Therefore, this is diverging by the divergent test. I've also heard this called the nth term test, because really what you're thinking about is what is the nth term, because the nth term, as n gets really, really, really big, must be 0 for this to have a chance of converging. I don't call it that. I actually sometimes do, but I'm calling it the divergent test for today, for this unit. So that's the justification that I'd like to say. If you just say somewhere that, hey, this thing isn't approaching 0 as n gets really, really large, then you're justifying the fact that it has to diverge. Alrighty, we're moving on. I wonder if I can do this. Yeah, I think I can do this. All right, we want to get our instincts down, folks. Instincts are important. You want to look at this because when you start proving something, you kind of want to have a direction. You don't want to be like, oh, I wonder if. You want to kind of look at it and say, I think it diverges or I think it converges. Now let me prove it, right? So my instinct is n over 2n squared feels like, if I kind of canceled it, 1 over 2n. And if I think of like 1 over n, my instinct is 1 over n. If it's like 1 over n, it's going to diverge because that's the harmonic series that diverges by the p-test. So we know this. Now we can come and say, well, let's compare these two. Well, this doesn't take too long. It doesn't take too long for us to get here. And the fact is, this is a non-zero constant. And if it's a non-zero constant, what that means is that the series of the numerator and the series of the denominator converge or diverge together. The denominator diverges, as we said, so therefore, by the limit comparison test, the series diverges. Oh, well, this is the same thing, isn't it? It's the same thing squared. Do I have to do this one? Yeah, it's the same thing squared. So this is like 1 over n here, right? But it's now being squared. So we're now just going to compare it to this. 1 over n squared. You know this converges by the p-test. P equals 2, which is greater than 1. And therefore, this could be 1/4, folks. A non-zero constant. Therefore, they converge together because we know the denominator converges by the limit comparison test. The series converges. Alrighty, 1g. Uh-oh. This one doesn't look so easy. part of the fun of me doing these problems is that, you know, I don't have my assignments in front of me. I don't have my worked out solutions that I did years ago. So I get to kind of experience this like you are and figure out, what are we going to do here? Well, I'll tell you, I look at this right away, and sine of 1 over n, as n gets really, really, really big, that's going to be approaching sine of 0. And sine of 0 is 0. So it's got a chance of converging. It doesn't diverge by the divergence test, right? So it's not geometric. I don't know. What are we going to do? Well, one thing that I can start thinking about is, I wonder if I have some kind of ratio. No, the ratio doesn't look great. Can I compare? Comparison test. Limit comparison test. I got it. Yeah, that looks good. We'll try this. Yeah, thank goodness we did all those trig limits. I think this is going to work. This diverges by the 2p test. Why the heck am I even thinking about that, right? Why is this even going through my head? Well, I'll tell you why it's going through my head. Because I spent all that time doing limits that I remember that I did stuff like this before. And I did stuff like this before because what we did is we did little subs where we did little u subs. I'll call it theta so we see our friend. Let's find our friend. It's been a little while since we saw our only friend. So what happens to, as n goes to infinity, what's theta going to approach? 0. And then we got sine of 0, sine of theta up here. And then we have theta in the denominator. That equals 1, which is a non-zero constant. A non-zero constant means what? It means that sine of 1 over n over 1 over n, this is kind of becoming our only friend. So therefore, the sine of 1 over n and 1 over n are both approaching infinity at similar speeds. Therefore, if 1 over n diverges, the sine of 1 over n also diverges. You know, folks, the kind of things that you have to start thinking about when you're looking at this. I mean, I look at 1H, 1G, and 1H, and I say, what the heck? In my head, I want you to know that I said, can I do that integral really quick? No, I didn't think I could do that integral really quickly. So I didn't go to the integral test first. I did see a quick root because, you know, there's nothing to the power of n. I didn't see a quick ratio because I thought sine of 1 over n plus 1 is not that great. So I went through the head thinking integral, ratio, and root tests aren't that great. And then I started thinking, well, maybe I could find something to compare. It's kind of like process of elimination sometimes. You don't have like 15,000 tests that you could possibly employ. You have, what, 8? So you kind of go through them piece by piece, and you kind of start narrowing them down to figure out which one you think you can best employ. The cool thing is, since we did that one, I think I have an idea how we're going to do this next one. Let's see. Yeah. We're going to want something. We're going to want something that gets to a non-zero constant, right? We don't want a 0, and we don't want infinity. We want a non-zero constant here. So let's leave this blank for a second. I mean, some of you will remember from doing this before, but let's leave this blank for a second, okay? And we're going to just leave it there momentarily. We're going to bring back our friend. So what we did, you know, imagine you have a theta or a theta squared or a theta cubed, something down here, but we don't know what it is yet. So what we learned, because our only friend has sine squared, right? That's what we learned as our friend. What we're going to wind up doing is we're going to multiplying it by 1 plus cosine squared, cosine theta plus 1 plus cosine theta to create our sine squared. I know I'm doing this kind of fast, but we've done this before. The question is, what needs to be here in order for this to become a constant. Well, if we have a theta here, that's not enough, right? Because we have two signs in the numerator. We have two of our friends, effectively in the numerator, two parts of our friends. We need two in the denominator. So what do we need here? That's going to make this equal 1/2, right? So we need theta squared here, which means we needed what here? Well, I guess we needed theta squared there, right? But what do we need way back here? Well, we needed 1/n squared. So therefore, we know that converges. We know that converges. And now we know that this 1 minus cos of 1/n moves at the same speed as 1/n squared, effectively, because they have this common ratio of 1/2. So therefore, we know that by the limit comparison test, 1 minus the cos of 1/n converges. Definitely not easy, right? Definitely not easy. But I hope that you saw the way I was thinking about why 1/n squared and not 1/n, because you had to figure out you wanted this number over here. You needed this over here. This here had to make sure it became a constant. It had to be 1. So that's why I chose that as my option. 1i. What is this? Wow. I'm going to hit pause for a second while I think. No, I'm not going to hit pause because at least it doesn't teach you, at least, or show you how I'm thinking about this. So let me tell you what I'm thinking. The first thing that I'm thinking is that the ln, it looks like the big term is going to be, as n gets really, really large, it's going to be about ln of 1, so it's close to 0. So it doesn't diverge by the divergence test. I don't think I'm going to go geometric. I mean, I don't see anything at all that's going to be geometric. I have another thing that I'm going to think about doing, but I want to see if I can come up with a test first. I'm going to try something, right? I'm going to try something just because I don't know if this is going to work, but we're going to try it anyway. So that is approaching 0, right? And if that's approaching 0, we'd love to have something else that is also approaching 0, because if we were able to do a limit comparison test, we could, if this was 0 and this was also approaching 0, right? If the denominator was approaching 0 as well, we could use L'Hopital's rule. This could fall flat on its face, folks. You maybe just see me watching me go down in flames, but oh well. Okay, let's see what happens when we do this problem. The derivative of this, if we did use, I mean, I'm just saying, imagine there's something here, right? Imagine there's something here, and we want this to be over here, some constant, right? Oh, way over here, we want this to be some constant, right? Way over here. That's what our goal is, right? Because then we know, if we can put something in the denominator that we know converges or diverges, we know that we get a constant, we know that they'll converge or diverge together. Okay, so let's take the derivative. Let's pretend that there's something here that goes to 0 and we can use L'Hopital's rule. Okay, so I'm going to take the derivative of this. Oh, that's not a pretty derivative, is it? Ooh, goodness. All right, so 1 over that times the derivative of the inside. The derivative of the inside, oh, the derivative of the inside is really just 1 plus 1/n squared, right? That's what the derivative of the inside really is. So that's just really, the derivative of that's going to be 0 plus -2 over n cubed. All right. Well, look at that. If I took the limit of this, that's basically, the n squareds are going to effectively cancel out, leaving me just -2 over n cubed. So if I had something here that was also n cubed, like something like this, if I did something over here such that this turned into some constant, this would just be, what, -2, which is a non-zero constant. So I have to figure out what here, when I take the derivative, gets me to this. Oh, that's just end of the... Oh, that's the same thing, isn't it? In fact, I can have a constant here, too. I'm just going to do this, folks. And then I can come back and say, yeah, I could have done that. I'm now choosing 1 over n squared to compare it to. Because now when I take the derivative, that's going to give me a nice negative 2 here. And then I make a nice 1, which is a non-zero constant. Which means that numerator and denominator are going to converge or diverge together. That means because... Where did this one start at 1? Yeah. Because this converges by the p-test, then is that right? I hope that's right. I think it converges. Okay, so now I'm going to hit pause and see if I did this problem in the years past. I'll be right back. All right, folks. So I decided to look through my older notes how I tackled that problem in the past. Couldn't find it anywhere. I said, wow, this one's a really, really doozy. So I tried a few things. In purple, I tried the ratio test. I felt like I was really doing something good. If you'll notice, I'll use a little red to mark. If you notice what I did here is that's a sub n plus 1. That's a sub n. And I took the ratio and I said, okay, I'll take the, when I'm doing a limit, I can use L'Hopital's rule. So I used L'Hopital's rule, took the derivative of the numerator, took the derivative of the denominator, and I got 1. So the ratio test is inconclusive. You don't know anything. So I said, there's got to be another way to do this. And I said, well, I wonder if I can do the integral of this. And I've said to you folks a few times, I like doing this in my free time. Well, here's the perfect example. I try to do this limit, and I try to do this integral, and this integral is a doozy. Long story short, I did parts. You'll see I did parts all the way through here. This was all my parts. And then after I did parts for this is like the indefinite integral over here. Then I took that indefinite integral, and I put it back into the... I try to evaluate it. So if you see, here is where I'm evaluating it. I plugged in b, and then I plugged in 1. These are all nice constants. This here, by the way, in case you were wondering, the inverse tangent of infinity is effectively pi over 2. So we're okay there. So that's just 2 times pi over 2. So we have 2 pi minus ln of 2 plus pi over 2. Okay, so these are all constants here. If this guy just here, as long as this guy right here can be some constant as well, we know that this converges, right? Because then the limit doesn't go off to infinity. If this limit doesn't go off to infinity, the integral converges, and the integral and the series converge together. So I evaluated this here, and I got infinity times 0. That's not really good. I turned it into a quotient so I could use L'Hopital's rule. Long story short, I may have made a mistake here, folks. I'm kind of flying by the seat of my pants. So I said, okay, what happened? That looks like it's going to be 0. And therefore, this overall expression right here is converging upon some number. And it's some number. I mean, we don't really need to know what it is. I think it's going to be pi minus the ln of 2 minus pi over 2, which I guess we can just write it like this. But, that's not important. Because just because what the integral is converging upon doesn't mean that's what the series converges upon too. The series is not converging upon this number. But we just know since it's converging upon some number that the series converges with it. So by the integral test. So yeah, that's a lot of work, right? And some of you are saying, Mr. Popper, there's no way I could do that myself. And that's fair. I don't think I expect you to do that blue problem. Frankly, and I'm not sure I would expect you on a test to do something like green. But it's kind of fun to do because it really makes you think. My initial instinct was, no geometric series, right? No divergence test, no root test, no p-series test. So it really left us with just what? Comparison, limit comparison, ratio, and integral. So they're the 4 tests that we were able to bring to bear. And sure enough, if you did the right comparison, the right limit comparison, it would work. And if you did the correct integral test, it would also work. Anyway, I'm going to stop here for a second, not because I'm going to stop. I'm actually going to keep going in a moment, but I'm going to pick up with, I guess, Jay in a moment. But I want to make sure I break up the video into 2 pieces for upload, as well as in case there's some kind of error. I'd hate to waste those 30 minutes that I just spent doing this. Okay, so I'll catch you folks in a second when I start on Jay.